All right. Good morning, everybody. Looks like we are ready to go. Let's see. Do I have an echo over here? Nope. That one's good. Okay. Excuse me. So, where are we? Well, we're working on chapter 5 right now, which is probability, right? And you can see this is due tomorrow. We have chapter 6, which is actually due in a couple days. I'm probably going to extend the homework for chapter 6 a couple days to give you a little more time to work on that. And then chapter 7 you would see is originally due the next day after that. So I'll give you a little more time for chapter 7 as well. This originally happened because I had to move back some of the assignments from chapter 5. But now then, if you move something, there's only so much room in the semester. So if I move something back, that means that, things get a little smashed together at the end. So we have that. I can space them out a little bit better now that we're here, but you got to make sure you're progressing through these. Sorry, I forgot to get rid of my gum before I started teaching here. So, so we're going over counting techniques today and sort of finishing off this chapter for probability. And then, like I say, this chapter 6 is short. There's only 3 sections from it. And chapter 7's shorter too, even though there's 4 sections there. They're kind of lighter a little bit. So I'll extend those due dates out, but they're still going to be done in the relatively near future and get that taken care of. Then we'll get into chapters. Chapter 8 is out there, which is important. And then chapters 9 and 10. You're kind of tying everything together from the whole course, right? And notice chapter 10, that's about as late out as I can push things because that's the end of the semester. So I can't push things out any further. You do have, where are we? You've got your conclusions coming up, but you still have a little bit of time before you have to turn that part in. And the rest of this stuff you have your correlation coming up soon. So for your correlation, right, you've got, I'll see you again, but you should start putting that together. So that is looking at you should be looking at R values. You should have a scatter plot in there. You should have a scatter plot that includes the line of best fit so that you can talk about if the line of best fit is a good fit or if it's, visually look at it. We looked at pictures like that. So you should definitely be doing that. Get your, get your correlation, your visual together, your scatter plot, your R value. It's definitely something you should talk about during the project. So tie it into, your project, however you want to do that. But that's one of those things, if it's missing, I'm going to go, why didn't they discuss correlation at all? And even if you have no correlation, right? I've had students that go, well, I can't include it because I didn't get an R value that's close to 1 or -1. But the information that 2 variables are not related can be as important as the conclusion that 2 things are related. So finding that 2 things are related, we would call that a positive result because you found a connection. So that's good. You could say, well, we found that, like, for example, work that's being done right now at the national level, we found that a lower income relates to life expectancy. That's good because that kind of discussion could lead to changes being made in a mental health, or not mental health, but a health perspective, so that you can try to fix that, so that we don't have people just because they're born into the wrong community, their life expectancy is shorter, right? So there's work like that being done. That's where you're tying together 2 variables and showing there's a correlation between those 2 things. But sometimes people might think 2 variables are related, and being able to show that in fact no, they're not related is also useful. We've done that at the college where we take a certain strategy and say, if we do this, then the students who were able to accomplish this in this class should probably be ready for this other class. And then we look at the data and it's like, no, those things are not related. Success in this one course over here does not necessarily mean you're going to do better over here. We've had some surprising results. And then we actually have to have these kind of statistical discussions like we have in this class where we go, wait, do we really think that those 2 things aren't related? And then we sit there and we, all the things we've learned about this class where we go, well, the sample size may not have been okay, and the way the data was collected is actually, even though it was collected automatically by computers, there's a little bit of, the way that it was done, the methodology may not be great, and then we can talk about it. So just because you have an R value that is close to 0, or maybe it's 0.4 or 0.5 or something like that, so it shows there's not a strong correlation, doesn't mean that you shouldn't talk about it in your project. Remember, you're not doing like publishable statistics here, right? This is an intro to statistics project. I'm not expecting you to be operating on the level of like grad students who are trying to publish the work that they're doing, right? Because you're new at this. Now don't take it the other way. I'm not saying like, oh, take it easy, don't put much work into this project. You should do good work, but what I'm saying is, remember that the point of the project is not to create a publishable thesis. The point of the project is to communicate to me what you have learned and what you have not learned over the course of the semester. So if you show me a scatter plot and the line of best fit that StatCrunch gave you, and the line doesn't fit your data very well, and you show me an R value that is, you talk about an R value being maybe 0.479, and you say, yeah, what we found was there's not really a very strong correlation between these variables. They don't seem to relate to each other. What I just learned is that you learned about correlation and regression, right? So you really want to include it either way. Okay, and sometimes even in publishable research, if you found that two variables we would expect to be related, you found a very low correlation, that's information. That's new information that we can act on. So I think when you don't find a connection, that would be considered a negative result from the way we talk about it in science. And students think, oh, well, it only counts if I find a connection between variables. No, that's not true, right? Like I was saying, we do that at the school level. So make sure you're putting those things together. A good scatter plot that you can explain for a couple of minutes in your project. I go, okay, that's a major topic of the class. This person understands what they're talking about. Good, right? So make sure you're getting that done and ready to go. That's due in the next week. So you'll want to be making sure that that's done. Remember, that's under chapter 4. So make sure you don't forget to go back there and answer that. Okay? All right, so we have to get into counting techniques, and then sort of putting this all together is actually not too bad. So mostly we'll spend the time today talking about those counting techniques when we're looking at this. So what is that about? What do you mean counting techniques? I know counting. I can count 1, 2, 3, 4, 5, 6. You can't always count that way. There are certain types of things that require special types of counting. There's really 2 reasons why you would have to count in this way. And I know I've talked a little bit about this before, but now we're really doing the dive into this section. One is because there's just too many possibilities, right? If we had a group of 5 people, and I say, okay, from this group of 5 people, find every way that we can pick a president, vice president, and treasurer. That number is small enough. It would take you a little while, but you could do all those combinations by hand, right? It would probably take you, 5-10 minutes, something like that. And you'd figure it all out and go, okay, here's the number of ways that we can make a president, vice president, and treasurer from this group. The other thing I could do is say, find all the ways to create a subcommittee. Now, that might seem the same. Isn't a subcommittee essentially the same as president, vice president, and treasurer? No, because in a committee, everyone's kind of equal. Everyone has equal position. Everyone has equal responsibilities, right? You're just a subcommittee working on something. Whereas if you've assigned people president, vice president, and treasurer, each person has a job. Each person has a responsibility, right? The treasurer is probably handling things that are money related. The president is probably making the big decisions and representing the group as a whole. And the vice president's usually kind of in the middle doing, whatever work doesn't fall into those other categories. The vice president has to go clean up those messes. So they're a little bit different. Like if we put you in a group that has specific roles, or we put you in a group of a bunch of equals, there's a different number of those things. So that's 2 separate problems I could give you. I could give you one to say, okay, from this group of 5, go find all the ways to make president, vice president, and treasurer. And then I could say, go find all the ways to make a 3-person subgroup from this committee of 5 people, right? Those are different problems with different numbers of outcomes. But they're small enough that you can do them by hand. Okay, but the sizes of these problems get very big very fast, like ridiculously big, to where we wouldn't have to get a very big group at all, say a dozen people, and I say, go find all the ways to pick a president, vice president, and treasurer from 12 people. It's going to keep you busy for I would have to sit down and calculate, like estimate how long I think that would take, but it would take you a chunk of the day to figure out. And by the time we get to like 20 people, forget it. You're not doing it by hand ever. It's not going to happen. So we have to figure out how to count these kinds of things, because one, the problem is too big, but also you can't count it by just going 1, 2, 3. I mean, you can if you make an exhaustive list and then you just see how many things are in your list. But like I'm saying, most of the time you can't do that because the problem is simply too big. Okay. So, and you might go, well, wait a minute. We're learning a whole type of probability just based on picking presidents, vice presidents, and treasurer versus picking combinations or subgroups of people? And the answer is yeah, because it comes up in a lot of other situations. We usually, when we're teaching this early combinations and permutations, we use this example of president, vice president, and treasurer, and then subcommittees, because people understand it pretty quickly. But comes up all the times, all sorts of times. It comes up in computer science, it comes up in science, they come up in business, all sorts of different places. You come up where you have to count certain types of combinations, and they almost always fall into one of these two categories, either a permutation or a combination. And being able to count those is very important. Okay? Partly because you don't want to confuse the two, but also otherwise you just aren't going to be able to get to an answer, right? So let's figure out what these mean. Permutations of items are arrangements in which different sequences of the same item are counted separately. For example, if we have the three items A, B, and C, and then we take the arrangements ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. So that's what a permutation is. And you'll hear people when they're first learning this, the question is always being asked, does the order matter? Does the order count? This is like a common thing for professors to be asking their students, because if the order matters, then it's a permutation. If the order doesn't matter, then it's a combination. So that's kind of you want to get in the practice of always asking yourself, does the order make a difference or not? So for instance, if I'm picking a president, vice president, and treasurer, the order matters, because when I make these lists in this order, like we can interpret this one as being A is president, B is vice president, C is treasurer, right? I'm in the yellow box. If you can't see the cursor, I'm over here. So if this was the order of president, vice president, treasurer, then ABC is different than ACB, because this would be A is president, B is vice president, C is treasurer. This would be A is president, C is vice president, and B is treasurer. So see how it's a different ordering. So we say, well, yeah, they have different jobs in this one, so it's a different assignment of duties. Therefore, these permutations are all counted differently. Okay? For a combination, we do not count them separately. We would say ABC, ACB, BAC, BCA, CAB, and CBA are all considered one count. And I go, well, wait, why would you do that? Well, again, this is the type of thing where you consider all those in the same order to really be the same, right? This would be if we made a subcommittee for this class, but all members of the subcommittee were going to have equal rights and equal duties in that subcommittee. Then it doesn't matter if you pick A, B, and C or BAC, you still have the same subcommittee, right? Like imagine if I was going to pay you $3, I owe you $3, so I have $3 bills. Does it matter which order I pay you the dollar bills? I mean, I could give them in order of serial number. I could give them in order of reverse serial number. I could give them in a random order selected by a computer. But who cares, right? It doesn't make any difference which dollar bill I give you first. But up here in permutations, we do care about the order of things, because it's a different meaning. Okay, so just kind of keep that in mind, because these are kind of the keys of the chapters, being able to think about that. And I know it's confusing at first. I remember being so confused by these terms and always forgetting which one's which. Um, so they give you a little mnemonic here. One is permutations position, combinations committee. So P goes with P, C goes with C. Permutations position, like president, vice president, treasurer. So when you're counting something like that where the order matters, that's a permutation. Combinations committee, because when you pick people on a committee, it doesn't really matter the order that you pick the three people. They're all equal members of the committee. So you end up with the same committee no matter which order you pick those three people, as long as it's the same three people. So permutations position, combinations committee. And if you can keep those straight, it really makes a lot of this a lot easier. Right. Okay, so some notation we have to get into. The factorial symbol with an exclamation mark denotes the product of decreasing whole positive numbers. For example, 4 factorial is 4 times 3 times 2 times 1 equal to 24. And we have a special case for 0. 0 factorial is equal to 1, right? If you just tried to use the formula on 0 factorial, you'd go, well, shouldn't it be 0? But no, we've defined 0 factorial to be 1. And you might think, well, why? Aren't you kind of cheating if you just define it to be 1? And the answer is no, because if you think about the factorial symbol as the number of ways of arranging that many items, which is how we're going to treat it, then 0 factorial would be 1, right? So 4 factorial is the number of ways that I can arrange 4 items, right? I take 4 different items, I put them on the table. What's the number of ways I can arrange them in front of me? 4 factorial, and I'll explain why that is in a minute. So by that same reasoning, 0 factorial should be the number of ways of arranging 0 items. Well, how many ways are there to arrange 0 items? I have 0 items on the desk. How many ways can I arrange them? 1. I just don't have anything arranged, right? That's the one way to arrange the items. There's nothing there. So it actually makes sense. If you forget that 0 factorial is 1, your calculations are going to get all messed up because it ends up in the denominator of a fraction. Can't have 0 in the denominator of a fraction, so it's gonna mess things up a bit. Let me pull up the calculator. So you should have a calculator in your computer, whether you're using the Windows calculator. Sorry, I forgot to drink a water this morning. Let me go grab one. I'll be right back. All right, thanks. I was starting to get the hiccups because I'm dehydrated, so. Okay. So, right. So you should have a computer built into or a calculator built into your computer. Whatever operating your system that you're using, whether it's Mac, Windows, or Linux, there should be a calculator in there. And I believe they should have factorial. So this is the Windows one. If you're not seeing it, you can go in there. You've got your standard mode, which does not have factorial in it. But if you just go in and change it over to scientific mode, you've got your factorial right here. So it's that exclamation mark. So notice if I do 4 factorial, sure enough, it says 24, just like it says up here, 24, okay? Now, factorials get real big real fast. Let's take even 9 factorial, big number, 362,880. Factorials get really big really fast. So you can see what I was talking about earlier where we end up with such a large number of calculations, it doesn't make sense that we can make an exhaustive list and then count the list, right? even for something like this, you could probably pull this off if you wrote a little program to write all the combinations and then calculate it from there. But we can get into factorials that are so big that a computer program would still take months to finish, but we can do it very quickly with the formulas that we're about to learn in this green box, right? So I've tried this on the TI-84. I don't remember if it works on Windows. Yeah, so this is 100 factorial. That's a number with 157 digits. So a large number, 157 digits, right? That's 100 factorial. Even 50 factorial, it's got 65 digits. You wouldn't want to write that out. In all likelihood, you'd make some kind of mistake if you were writing it out. So really, really big numbers. Too many combinations for us to find by hand. Okay. Which is why we have formulas for figuring them out. Okay, so the fundamental counting rule we've already learned, right? This came up in the last sections. M times n equals the number of ways that two events can occur, given that the first event can occur m ways and the second event can occur n ways. This rule extends easily to situations of more than two, right? So more than that. So for instance, where are we here? If we go here, go up here. Right, let's just take A, B, and C. Right, and we're going to find, when you do these problems where you can do them by hand, where you can count them by hand and just make a list, you want to be systematic about how we do that. And usually what you'll see is the way to do that is to change from the back end of your combination and force your way to the front. And then what'll happen is you can create a pattern of how you're moving through these. So let's see, I wanted to go through the order of A, B, C. Okay, so we've got A, B, C, that's one ordering. Then I want to move to the back. Okay, so how can I make a change? Well, I want to change that C to something else. Well, then it could become the B. So it would become ACB. See how I changed the last one and then that caused the second? You always have to move two because you're switching them. Okay. That's all the combinations that are possible where you start with an A. All right, well then let's start with a B. Well, we could have BAC. And then the other one that starts with a B would be BCA. Okay. All right, that's all the possible ones to start with the B. Now what about the ones to start with the C? You go CAB. And then CBA is the last one. So you're just systematically going through the list here. That's like what we're looking at. But one way of thinking about this is we can do bigger problems without making this list by thinking, well, how many choices do I have for the first position of my order? Just think about, like, if we're trying to figure out where this multiplication rule came from. How many different choices do I have for the first position? Well, there's three, because there's three letters, A, B, and C. So if I'm going to create a combination of A, B, and C, for my first position, I have three choices, right? Three. We have three positions that we're trying to fill here. Think of each of these parentheses as a position we're trying to fill in order to get one of these combinations. So I have three choices for the first position, right? Either an A, B, or C. How many choices do I have for the second position? So just think about that for a second. How many choices are there that I can put in position number 2? And the answer is there's 2, right? Because there were originally 3 choices, and I just picked one and put it in the first spot. So now I only have 2 choices left for the second position. So this one's going to become 2. I have 2 choices left. And then for the last one, we would say you have 1 choice, which most people would say, well, if you only have one thing to choose from, it's not really a choice at all, right? But that's sort of the language that we use. So there's 1. So the number of ways that we can arrange the letters A, B, and C should be 3 times 2 times 1, which is equal to, we would write this as 3 factorial, which is 6. When it's a small factorial like that, we just write out what it is. It's silly to talk about 3 factorial when I could just use the word 6, right? But when it's really, really big, like 70 factorial, then you're probably going to write it as 70 factorial because you don't want to write out a 100-digit number. That's ridiculous, right? So see how we did it by hand and we got 6 combinations, and then see how we used the formula and we got 6 combinations. So the formula is matching what we got here. So that's what they're talking about right here. The fundamental counting rule says we multiply the number of these objects together. So here's an example that might seem a little bit more interesting, hopefully. I think it's an interesting way of counting. Think about the number of license plates. So California license plates for a car, like a Corolla or some kind of car like that. Now, like with trucks, there's usually a different combination, and with commercial vehicles, there's a different combination. If you've ever paid attention to this, for motorcycles, there's a different combination. So let's just take the one for like normal automobiles, like SUVs and cars, passenger vehicles. You have what? I think you have a number, and then 3 letters, and then 3 numbers again, I think is how it works. So then the question we would want to ask is how many license, I always mess up the word license, how many license plates of the form number, letter, 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 number, number, I think is how it is. Okay, so how many license plates can we make? This is important if you're California and you have millions of people on the road, and what happens is they occasionally run out of license plates, right? So then it's this whole big project where the DMV has to come up with a new pattern of license plates. But you want to know, like, how many license plates can we come up with that? Because you want to be able to project before we put this into use. We want to know, is this enough license plates to last us the next 2 years? Or is this enough license plates to last us the next 10 years? Right? Because that tells you when you need to like redo the project again. So you want something that's going to last you a while. So how many license plates? Well, the state of California wanted to know, like this literally was being calculated by the people who set this up. How many can we come up with of this form of number, letter, 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 number, number, number? Okay, well, let's use the reasoning. It's actually an easy calculation. Let's use the reasoning that we just used up here. Okay, so we have what, 7 spaces? So 1, 2, 3, 4, 5, 6, 7. 7 spaces for our license plate. And one difference to note, remember before, I think last time we talked about with replacement and without replacement. Well, the problem we just did up here is without replacement, because you're not going to pick the same person to be president, vice president, and treasurer, right? That you just normally wouldn't do that. So you're trying to pick distinct individuals. Well, down here on a license plate, you'll see that license plates are allowed to have repeat numbers, and they're allowed to have repeat letters. So up here, remember how we had to keep reducing our options? Well, down here, we don't have that because the numbers aren't reduced. Just because you have a B in one part of your license plate doesn't mean you can't have another B in there. So how many of this form? Let's see. It starts with a number. How many numbers do we have? Well, we have a base 10 number system, which means we have 10 numbers that we use to represent numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the symbols that we use. So I have 10 choices for the number part. All right, now we need 3 letters. How many choices do I have for a letter? Well, there's 26 letters. So I have 26 choices here, 26 here, and 26 here, because we're saying once you use a letter, you can use it again. Okay. And then how many choices do we have for the last one? Well, the last ones are numbers again. So 10. Oops, that's 19. 10, 10, 10. So right here, we're using that multiplication property, right from here, the fundamental counting rule that says we multiply the number of ways that an event can occur times the n ways the second thing can occur. So we're taking the number of ways these things can occur and we're multiplying them together. So now I take my calculator and I do 10 times 26 times 26 times 26 times 10 times 10 times 10 equals, and we get 175,760,000. And I don't know why it's not formatting right. Let's recompile here. There we go. Finally got it in there. Now my calculator's gone. There we go. So 175,760,000. Pretty easy calculation just using that fundamental counting multiplication rule. That's all it took. But like I mentioned before, with replacement and without replacement, you have to be the one to decide, oh, this problem up here is without replacement. This one down here is with replacement, right? So 175 million license plates. Of course, they go through and they eliminate some, like the 3 letters. If it phonetically sounds like a bad word or something, they pull those out, right? So, you know, you can imagine what I'm talking about, but they go through and they pull out the ones that if you can put in here and it either spells a bad word or it sounds like it's a bad word, they eliminate those ahead of time because a lot of times people complain about them and stuff. Okay, so that's that fundamental counting rule that we're talking about right here. Okay, factorial rule. The number of different permutations, order counts of n different items when all n of them are selected. This rule reflects the fact that the first item may be selected n different ways, the second may be selected n-1, and so on. So that's like the example we just did with the A, B, and C. And we go, well, wait a minute. I thought you said that was the fundamental counting rule. Well, it is. This factorial is the fundamental counting rule being applied to a problem where you do it without replacement. Because notice we did still just multiply the spaces together here. 3 times 2 times 1. It just happened that those numbers were going down by 1 each time, giving us the factorial. Okay, so it's one of these things where the calculations aren't that complicated, but one of the hard thing is figuring out which calculation are you supposed to use. You have to be comfortable enough with this to ask yourself, let's see, should I be using the fundamental counting rule or should I be using the factorial rule? Which you could argue in some instances, you could argue you're using both, but you don't want to use the factorial rule for a license plate problem. That's not going to work. Right. Right. We have to count those a little bit differently. Okay. Then we have, man, they're giving us all the formulas right at the start. We'll talk about these and do some examples. So we have the permutations rule when all of the items are different. So this would be where you have like distinct items, right? So I've got maybe phone, keys, wallet, what else would a person have? I don't know, some money. So just you got some cash in your pocket. So phone, wallet, keys, and then some cash. Like, what are the number of different ways that you can pick a few of those things? So from those 4 items, what is the number of ways that I can pick 3 of them? Well, here's your formula right here. And this is a pretty common notation. Even if we go to Wolfram Alpha, like see how it's NPR is the number of different permutations when n different items are available, but only r of them are selected without replacement. So we were kind of doing something like this up here, but we were using everything, right? So for instance, when we did our A, B, and C, we were using all the letters available. We had 3 letters available, and we were coming up with the ways of arranging all of them. Well, what if you had 5 letters available, but you wanted to know all the ways of assigning 3 of them? So this would be the example if you have, like this would be, how many different ways can you pick a president, a vice president, and a treasurer from 3 people? So let's say your club is not very popular. There's only 3 people in it. And you want to figure out how many ways can we name ourselves president, vice president, and treasurer? Well, the answer right here, there's 6. But what if your group grows and you have 5 people? What are the number of ways that you can come up with 3-person assignments from the 5 people? Well, it's a little bit different calculation. And that one you actually can still do using, well, I don't want to confuse things. But see how they put it in here as NPR? A lot of these softwares are actually designed this. So even if we go to Wolfram Alpha, which is an online computation engine, calculates things, right? Google's a search engine. It finds things. Wolfram Alpha is a computation engine. It calculates things. So even if we go on here and I use that same lettering that they just did, so let's say I did 5P3, right? Because that's what they're showing us in the book, an N and then a P and then an R. So N is the number of items available. R is the number that you're choosing. So this is the number of ways that I can pick 3 things from a group of 5. Okay, so you technically, it's this formula right here, which isn't too bad. You just calculate it. But we'll see on Wolfram Alpha, they're going to tell us that's. The answer is 60. 60 ways to do that. See how these numbers get pretty big pretty fast? You're like, wait a minute. If I have a group of 5 people, the number of ways that I can pick president, vice president, and treasurer is 60. I think that's right, assuming I did that right. So let's calculate it by hand. Let's see what this formula looks like. So you've got n factorial, so your n is given here in the problem, over n minus r factorial. So if we want to do that, that's going to be, let's make a fraction here. That's going to be 5 factorial over 5 minus 3 factorial, right? That's the n over n minus r. Notice that the factorial is on the outside of the parentheses. You have to do the parentheses first. You can't like distribute the factorial in. That doesn't work. So 5 minus 3 is 2 factorial. 2 factorial is 2. So this is really 5 factorial over 2. And 5 factorial is 120. Which now gives us our answer of 60, which is what Wolfram Alpha told us it was going to be, right? So here I'm using the formula directly. Here I'm having Wolfram Alpha calculate it for me. You can do both, right? I'm not saying you have to do every one of these using a calculator, but you should be able to use the calculator, right? You don't want to get down the road and be like, wait, I never found where that factorial button is. You should learn how to use your calculator. It's really annoying how calculators are not consistent. Every company that makes a calculator does it differently than the way everyone else has done it. Like they're literally like it's pretty standard in classes. We use the TI-84, and then sometimes someone will bring in a Casio, and it's like it was developed on a different planet. Like everything is called different things. The menus are all set up differently. You can't find anything in it. So it's important, if you're going to rely on a calculator, make sure you know how to use it a little bit, okay? And Wolfram Alpha is kind of a fancy calculator. Okay, so that's when the items are different. Now we can also do permutations rule when some items are identical to others. And this looks like a totally different formula because it is. So the number of different permutations when n items are available and all n are selected without replacement. Okay, but some of the items are identical to the others. Right? So one example that people do is a word with repeated letters, right? Now, this is just to help you. This is not something practical that most of you would be doing in everyday life, but it's to help you understand what we're talking about when I show you this formula. So what if we wanted to know what are the number of different ways that I could spell the word boss? Okay, so we've got B. Actually, I want to do it this way. I've got B-O-S-S. And really, we have 2 different S's, right? So you've got the word boss, but notice we have 2 S's, but those things are really identical. So in the way that we read words. So what if I was to switch those S's with each other? B-O-S-2, S-1. Oops. Now, in this case, we could say, well, I see the difference, but normally we don't put subscripts on our letters, right? So imagine it just said boss and boss. You'd go, well, those are the same word. So if the question is how many different ways can I arrange a B an O, an S, and an S in order to get different words, then we would treat these the same. Now, when we say words in these types of probability problems, we just mean a collection of letters. We don't mean that it has to be like in the dictionary, okay? So these would be considered the same, but of course, if I went through and I did, and I made a change so that it was S sub 1, O, B, S sub 2, then, of course, this is the same letters, but in a different order. Of course, this one makes a different word, right? It's now sobs instead of boss. So these first two would be considered the same. This third one would be considered different because it's creating a different order of letters, right? So how on earth, that would be a pain to count, right? Yeah, it kind of would be a pain. But we can use that formula to figure out exactly what it would be without having to make an exhaustive list of all of them. So according to that formula given in the book, it's the total number of items available, which is 4. So 4 factorial. And then you divide by the repeats. So when the numbers are repeated, you divide by that. So see how here in their example, they have 4 A's, 2 B's, 2 C's, a D, and an E. So under here, they're dividing by 4 factorial, 2 factorial, 2 factorial. That's your repeats in the factorial. Because if we look at our word here, there's 2 factorial, or 2 ways of changing these S's with each other that give us the same word. So we're dividing those out. So it's really 4 factorial divided by 2 factorial, which is going to be, what, 20 divided by 2, so 10. 20 divided by 2 equals 10. So there are 10 different ways of arranging the letters in the word boss that give you a different arrangement of letters. Okay, 10 ways to do that. So you'll see this. It's very common. Unlike probability tests, they'll take like, how many different ways are there to arrange the letters in the word Mississippi? And so you go, okay, what is there? 11 letters in the word Mississippi. And then you have to divide out the I duplicates and the S duplicates and the P duplicates. And it's just an extended version of what we did here. Sort of a harder version of it, or larger version, I guess, to arrange those. So that's where this one comes from, this permutation rule where some items are identical. I know it's a lot to keep track of. Honestly, that's like half the battle with probability, is just being able to keep like these 5 things straight, right? Keep those calculations straight. And then we have our combinations rule at the end. And it looks just like our permutations rule, except there's an identical thing here. And this actually is logical. This is how I remember which formula is which. Is the combinations, we're dividing out all the different orderings of a similar combination. So remember, with combinations, ABC is the same as CAB. So what this R factorial right here is that you're dividing out, that's the number of different ways to arrange those 3 letters. So you count A, B, and C being collected, but then you divide by, in this case it would be 6, all the different ways that you can arrange A, B, and C. So you're just getting the different committees, not the different ways of assigning president, vice president, and treasurer. So that's the formula that you would use in that case. So you just have to read really carefully in the problem, because a lot of times, or pretty much always, they're not going to say, use the permutation rule here. Use the permutation rule with identical items here. Use the combinations rule. You have to think through that piece. And in real life, that's challenging too, trying to sit down and go, okay, what do I have here that I'm dealing with, and I need to calculate these probabilities, right? That's definitely a type of thing you can come up with. That's why they have, like, here's an example. They talk about choosing PIN codes. So your personal, like, you know, you've got an ATM card, or you have different accounts, and they make you have like a PIN number. Well, with 4-digit numbers, how many pins are there? Well, if you have 10 choices and a 4-digit pin, that's 10 times 10 times 10 times 10. So that's what? 10 times 10 is 100, 1,000, 10,000. That's 10,000. So a person's not going to guess it. And they usually require that you can't repeat stuff. So you can't go 0, 0, 0, 0. There was I think it was probably around 2004. You know how the companies always have these big leaks of information. They get hacked, and then all this information gets out. Well, I don't remember who it was, but somebody got hacked, and basically PIN codes were given out. And it's shocking the number of people whose PIN code is either 0000 or 1234 or 9876 or something like that, memorable. It was like massive numbers. I think it was something like close to like 20% of people use 0000, and then like another 20% use like 1234. Well, if you're using those, you're making it awfully easy to steal money from your account. So that's why most of those banks now are like, you can't have 0000 as your PIN code. You can't have 5555. You can't have 1234. You can't have those basic ones, because then all of a sudden all the ones left are like, there's a lot less probability that someone's going to pick it before. What is it? If you get your PIN wrong 3 times, they lock you out for 24 hours or something like that. So it's very unlikely someone's going to do that. But if you just find, and I'm obviously not suggesting anyone do this, but if you just found an ATM card and you were a criminal, you could go and you could, within your 4 checks, you could check 0000, 1234. Back in the day when this kind of stuff was still allowed, you could check those, and there's like a 40% chance you could get $400 out of somebody's account, right? Because usually it's 400. There's usually a daily limit on these as well. Is another reason they don't want people clearing your account out. So, it can be helpful. Like, this is real world stuff where people have to sit down. If you're making license plates for the state of California, or you're making PIN codes for your bank or whatever, how you go through and you pick these, it uses, or the options that you give people, you have to use these counting methods in order to make sense of that. Okay? So it looks like we're out of time. I think you can finish from there. I think we got, let me see if there's anything else. I think we basically talked about it. We did some examples. Yeah, there's the lottery. Lots of different stuff here. So good examples. Yeah. So that basically wraps up the probability. Next time we talk, we'll get into the next material. Remember, I'm going to slightly adjust, not this chapter, but those next 2 chapters. I'm going to make a little bit of adjustment to those so that you don't have to try to get those 2 chapters done in the next 2 days. But it's not a ton of time, because we don't have that much time left in the class. We've got, I think the class ends in a month, and then we have a final exam. So we still have to move through stuff pretty quickly. But that's where we're at. So anyone who wants to talk to me, please hop into Zoom, and I will answer any questions that you have. And otherwise, stay alert as to due dates. And remember, there's that one coming up. You still have some time, but you've got your correlation stuff you should be getting together to present in your project. Okay, thanks, everybody.